Hi, I'm Cruz Hinojos, and I'm the Regional Sales Manager for Bruker Optics. I have here the LUMOS Infrared Microscope. It is the most innovative infrared microscope on the market. As you can see, it is fully self-contained and standalone. As such, has fully integrated interferometer, infrared source, and detector. It is also a completely automated system. The reason for this is for ease of use, as well as making precision measurements. Okay. By full automation, I mean that you can automatically switch between visible modes, in which we have a high-resolution camera that can take very fine pictures, and an infrared mode to acquire your spectral information. Okay. All of this is controlled via one software. Okay. Therefore, you have full control over the system. Okay. You can see here a very large objective. Most standard microscopes have an objective turret that you switch and turn to for the objective of interest. Here, however, we have a single large one. It is large because in order to achieve a high numerical aperture. And basically what the numerical aperture is, the larger numerical aperture, the greater light is collected and the better sensitivity you have and the faster measurements you can take. Okay. This is actually a 4-in-1 objective. It can collect high-definition images, as well as in the infrared range, it can take transmission measurements, reflectance measurements, and attenuated total reflectance measurements. And I'll explain to you in a minute what I mean by attenuated total reflectance. This is an automated stage here, so you can actually do mapping and get chemical maps of your spectra. Okay. Also, what you can see here is there's a large degree of play in between the objective and the motorized stage. This allows you to put samples of differing ranges, differing size ranges within a sample compartment. Okay. Now we're going to look at the software real quick. Here we have actually an odd-shaped sample, actually a piece of rubber, and there's contaminant on this rubber. And if you can see in the screen here, the light bronze area is the contaminant, and the gray is actually the dark rubber. Okay. Now I'm going to take a image of a larger area, and you can see how simple this is. All you do is select the first border point, move over to another border point, add a new border point, and collect your defined image. So you can see our contaminated area coming up quite nicely. Now we're going to go back to our area of interest here. And we'll do it right here. Okay, and take another image. One of the cool features of the system is it allows you to acquire large panoramic images as well as a smaller image that I'm going to show here. Just a quick fine-tune of the focus. And now single image. If you want to go even higher magnification, you can activate zoom mode. And now you're even closer into your sample. A little fine focus. And now you have your zoomed in. You can also, so this is always your live view, and this is your static view, and you can actually toggle between the other images. Okay. And we go next, and we're going to measure our sample areas. To do so, you just simply drag, and now you have your sampling grid. This is actually very cool. Each red square is the sampling area. Okay. If your sample does not fit a nice square grid like that, you can modify your apertures. Okay. What each square is the analysis area. Okay. So you can actually make it smaller or larger. There we go next. Name the file. Now what you're going to see now is a automatically switching between the visible mode and the infrared mode. Okay. And you're going to see automated apertures come down and adjust according to the apertures we've made here. Okay. Here they come. So those are the apertures. Only the area inside the green square will be analyzed. Okay. All right. So it will now go through each one and collect a spectrum at each point. Now what do you get after something like this has actually occurred? You get data like this. Okay. The blue dot there corresponds to the blue spectrum here. The red dot corresponds to the red spectrum. So the red dot is in our contaminant area. Okay. And what I did was I took the area of a peak that was exclusive to the contaminant area and took the area of that peak. And that's what's shown here in this heat map. So large area, large value in the white and the pink. Low area, low value, it's blue. And in this manner, you can see in this three-dimensional depiction the distribution of that contaminant. So that is what I meant earlier by IR mapping. Okay. And as you can see, if you look down here, the ATR is actually coming in contact with that sample. This gives you the maximum amount of sensitivity because no light is lost. All the light's coming off the sample is going directly into that ATR crystal. Now the tip of that crystal is actually 100 microns. So if this aperture was fully opened, your resolution would be 100 by 100 microns. But with this system, it's so sensitive, you can get that down to 5 by 5 microns. So very, very high spatial resolution. Okay. Now while this is running, we can look at a couple of examples. Okay. Here is an electronic here. This is a image sensor. And the white and the blue, the speckled marks are just the standard image sensor. And the dark parts are the contaminants. You can see our red triangle there, that's the analysis area. And if you go down here, you see in this spectrum here, the red spectrum is the analysis of the clean area. The green spectrum is the analysis of the contaminant area. And the blue for each is a library spectrum. This actually identifies that particle there to be a polyamide. So either a nylon contaminant or even a biological contaminant on this electronic sensor. Here's another example relevant to the electronics industry. This is a choke for a surface mounted device. Okay. And then here we have these dark areas that shouldn't actually be there. Okay. So similar to what we did over here, we did actually a line scan going across. So instead of a grid of measurements, we have a line scan of measurements. And it was also a polyamide. And they took the areas of those polyamides. You can see the high areas here and there, indicating that you have a biological contaminant on that choke. Okay, one more example. This is a gold filter. The tiny particles there is just the pores within the filter. And the dark spots there are where we are what's caught on the filter. And you can see through here, one section of it, you have one of these particles being cellulose, microcrystalline cellulose. So that's one application I've seen a great deal in failure analysis is what's on these filters. Okay. All right. So we'll go back and see how our analysis is being done. It just completed this one right here and going on to this one and this one. So it's almost done. Note that in this example, we only modified the shape of one aperture there. So it doesn't matter, we could have modified every one of these 16 apertures differently depending on the sample. So you're not playing around with the sample inside on top of your stage here. You're adjusting those apertures to fit your sample and not the sample to fit your system. Okay. It's almost done. All right, on the last one, it should take about 16 seconds to finish. In doing so, with ATR, since you're touching the sample, it's possible in some samples that you see the touch marks. And seeing is believing. You know you've analyzed that sample because you've actually touched it and you see the indentation on that sample. Okay. And that will end. Okay, now it is ended, and we can go ahead and do a quick analysis of the data. Integrate. All right. And that is it. We have our chemical map here, and we have our image points to the right.